Welcome back to Extra, Gordo, WB6NOA. I have a special guest for all of you. Let's tune in now.
Good morning to all the students there taking their extra class test. This is W7AEG.
See, I have a ham friend talking to you this morning on the air.
Since I was 12 years old when I first got my general class equivalent ticket back in those days.
And Art has been a ham for almost 60-some years and really enjoys the freedom of the upper class licenses. Now, also out there in Radio Land to say good morning to you is my friend, actually best man Bill, WA6CAX. So, Bill, I'll let you say hi. Go ahead, Bill.
Hi there, this is Bill, WA6CAX in Sacramento, California. Good luck on your extra class test.
See, you have everybody pulling for you, so you're going to do just fine. And this is tape number 4. So here we get started with E5FO1, all about skin effect. Now, my two ham friends, Bill and Art, that you just heard from, were talking on mobile antennas with big coils. And the reason they use big coils is because of skin effect to reduce the amount of I²R losses or resistance in the coil. Because with skin effect, as we go higher in frequency, RF currents flow in a thinner layer of the conductor closest to the surface. And what causes the RF current to flow along the surface of a conductor? That is skin effect. And where does almost all of the RF current flow in a conductor? Along the surface of the conductor, especially at higher frequencies. And why does most of an RF current flow near the surface of a conductor? Skin effect. And why is the resistance of a conductor different for RF currents than for direct currents? Because of skin effect. Remember when they told you there would be 800 questions on the extra class pool, and you were going, oh my gosh, 800 different questions? Right now, we just had 5 that aren't different at all. Skin effect. Now let's turn our attention to static and a device that's used to store electrical energy in an electrostatic field. That device is, that's right, a capacitor. What unit measures electrical energy stored in an electrostatic field? That is, the unit of energy is the joule. What is magnetic field? Well, a magnetic field is the space through which a magnetic force acts, the field. In what direction is the magnetic field oriented about a conductor in relation to the direction of electron flow? Well, in a direction determined by the left-hand rule, where you grab the conductor with your left hand and the thumb points to the direction of the electrons as they're flowing in the conductor. And what determines the strength of a magnetic field around a conductor? The amount of current. More current, the greater the magnetic field. That's why mariners always keep any high current carrying conductors away from their ship's compass. What is the term for energy that is stored in an electromagnetic or electrostatic field? That is called potential energy. Potential energy. Now let's take a look at circuit Q, reactive power, and power factor. Time to take out a writing instrument because we want to write down this formula. Q is equal to R over X sub L in a parallel resonant circuit. Now, parallel, not series, that's different, but in a parallel resonant circuit, it is Q equals R over X sub L. Parallel. What is the Q of a parallel RLC circuit if the resonant frequency is 14.128 megahertz and L, the inductance, is 2.7 microhenries at 18 kiloohms? Well, we're looking for the Q, or quality of a circuit, where the resonant frequency is known, the inductance is known, and the resistance is known. Now, in parallel resonant circuits, as resistance increases, And again, this is in parallel resonant circuits. As resistance increases, the Q decreases and the bandwidth increases. As resistance decreases, the Q increases and bandwidth becomes sharper, which is usually what we want in an antenna-tuned circuit. Remember, this is a parallel resonant circuit. But before we divide the inductive reactance, X sub L, into resistance to find out the Q, we first must calculate the inductive reactance. Now, calculating the inductive reactance is easy as long as you keep your decimal point positions on target. And I'll show you a shortcut. Now, the frequency in this problem is given in megahertz, and the inductance is given in microhenries. In fact, all of the upcoming problems, megs and micros. Since we're multiplying these together, X sub L is equal to 2 pi times F in megs, L in micros, they cancel. So it's a simple multiplication of 6.28, that's 2 pi, times the frequency, 14.128, times the inductance, 2.7, equals 239.55. Now write that down, clear that calculator, and 18,000 divided by 239.55 comes out 75.14. And that's your answer, 75.14. That is the Q of this circuit. Now let's try another one. What is the Q of a parallel RLC circuit if the resonant frequency is 4.468 megahertz? That's a strange one. 4.468, okay. L is 47 microhenries and R is 180 ohms. Let's first calculate X sub L is equal to 2 pi FL. So 2 pi is 6.28 times the frequency, 4.468, times 47 equals 1318.8. Now, divided into 180, and I'm doing that on my calculator, comes out 0.136, and that is the answer to this question, 0.136. Now let's try another one. What is the Q of a parallel RLC circuit if the resonant frequency is 7.125 megs, L is 8.2 microhenries, and R is 1 kilo ohm, 1,000 ohms? No problem. First, we will do 6.28 in our calculators, X 7.125, X 8.2, and we're going to divide our answer after hitting the equals mark into a resistance of 1,000 ohms, and that comes out, that's right, 2.72. Let's try another one. Q of a RLC circuit, resonant frequency is 7.125 megahertz like above. L is 12.6 microhenries, R is 22 kilo ohms. 6.28 times megahertz times microhenries, and divide that into 22,000, and that comes up, yep, there it is, 39, and that is the correct answer, Q of 39. What is the Q of a parallel RLC circuit if the resonant frequency is 3.625 megahertz? I got my voice back, but now I can't speak. L is 42 microhenries, and R is 220 ohms, no problem. 6.28 X 3.625 equals sign, X 42 equals sign, 956.13. Now, on your calculator, hit the clear button, enter 220, hit the divided by sign, 956.13, the equal sign, 0.23. Gee, another answer less than 1, but that agrees, yep, 0.23. That is the Q of this particular circuit. So X of L is equal to 2 pi FL. That is an important formula to remember because you're going to need that when you divide X of L, which is equal to 2 pi FL, into the resistance given on the problem to calculate Q. Be sure you're dividing the bottom into the top, not the other way around, or else you'll end up with an answer that they may be waiting for you to go for that's incorrect. So watch out. You may be assured that I have discussed with the question pool committee that makes up these questions and answers, why give us an answer that if you do the division backwards, you're just waiting for the applicant to go for and it's wrong. And they say, well, it's part of knowing all about these things. Well, I tried, so be very, very careful. As you do your calculator keystrokes on going from the bottom into resistance, it's just opposite to what you might think of as you're looking at it. On this last question, you press and hit the clear button, and then you enter the numbers 220, that is the upper, that is the resistance, divided by 956.13, the equal sign, and that comes out 0.23, and that's how we calculate that as the correct answer. But if you do it backwards, if you divide 220 into 956.13, you're going to end up with 4.35, and they've got an answer there on the exam. You think, boy, I did it just great. No, you didn't. You missed it. You did it backwards. So be very, very careful on these Q problems that you know exactly how to use your calculator to work these out. Now let's do about 4 more. Let's jump forward and try this one. What is the Q of a parallel RLC circuit if the resonant frequency is 14.128 megahertz, L is 4.7 microhenries, remember megs and micros cancel, and R is 18 kiloohms. Now, let's do this on a calculator just to make sure that you know that the numerator, that's the top one, is divided by the denominator, which is the bottom number. The denominator is what we calculate, X of L is equal to 2 pi FL. Numerator is the resistance. All right, on this one, we're multiplying 6.28, which is 2 pi, times 14.128, which is the frequency in megahertz, times 4.7, and that comes out 417. Now, be careful. 417 is on the bottom. That's a denominator. Remember, numerator divided by the denominator. Now, on our calculators, hit the clear button, and we'll do this one together. I just want to make sure you don't get them backwards because they're just waiting for you to get them backwards. On the calculator, we first enter, that's right, we first enter the resistance, which is 18000 divided by 417, and we hit the equal sign, and we end up with 43.165467. That's it, 43.1. Okay, good job. Now let's try one more. Resonant frequency is 14.225 megahertz. L is 3.5 microhenries. R is 10 kiloohms, no problem. 6.28 times the frequency, 14.225 times the inductance, 3.5 microhenries, ends up 312.67. Now on your calculator, hit the clear, and what's the first thing we put in? That's right, it is the numerator, which is the resistance. 10000, then hit the divided by key, 312.67, hit the equal, and it comes out 31.98. Let's try another one, okay? Frequency 7.125 megahertz, L is 10.1 microhenries, R is 100 ohms. 6.28 on your calculator, X 7.125 equal sign, X 10.1 equal sign, 451.92. Hit the clear button several times. Now we put in the numerator, that's 100. Hit the divided by sign, 451.92, and that equals 0.221, the correct answer. All right, one more. The frequency in this one is 3.625 megahertz. L is 3 microhenries. Megs and micros cancel. R is 2.2 kiloohms. See, they're trying to catch us on this one. No problem. 6.28 times 3.625 equals times 3 equals 68.29. Then clear your calculator after you've written down 68.29. Hit the clear button several times. Clear, clear, clear. 2200, which is the same as 2.2 kilo ohms. Hit the divided by sign. Your calculator blinks. 68.29. Hit the equal sign. There it is. 32.215551. 32.22. There, I've done it with you. You see, I too am not great on math. I'm not a physics instructor or a math instructor. So that's why having that calculator handy and knowing that the numerator, that's the top one, is divided by the denominator, that's the bottom one, and that comes up with the correct answer. But be careful, they're waiting for you to make a mistake, and they've got a wrong answer just waiting for you. I don't think that's appropriate, but there you go. All right, now we know that particular one, the Q. Now let's go to a little verbiage about that. E5G06, we'll jump back just a little bit in the book. Why is a resistor often included in a parallel resonant circuit? Well, in a parallel resonant circuit, a resistor is added to decrease the Q and increase the bandwidth. Now, in the circuits, we sometimes have inductors and capacitors. What do they call the out-of-phase, non-productive power associated with inductors and capacitors? We call that reactive power. And that is power out of phase. It's non-productive. And in a circuit that has both inductors and capacitors, what happens to this reactive power? Well, it goes back and forth and back and forth and back and forth and back and forth between magnetic and electric fields, and it's not dissipated. Key words for the examination goes back and forth. In a circuit where the AC voltage and current are out of phase, how can the true power be determined? Well, we need to do that by multiplying the apparent power times the power factor. And they give you one question where they want you to bring that scientific calculator and work it through its paces. You don't have to. The question is, what's the power factor of an RL circuit having a 60-degree phase angle between voltage and current? As long as you remember that 60 degrees, given in this problem, comes out 0.5. Now, in my book, you can see a little diagram that shows you exactly what this apparent power, true power, and reactive power is all about. It's found on page 136. And just remember, 60 degrees is 0.5. 0.5. Now, how are you going to remember that? Well, just think that throughout most of the country, you can only drive, as you're listening to these audio cassettes, 65 miles an hour. 60.5. By the way, where are you listening to my audio cassettes? Sometimes I get readers that will email me at wb6noa.arrl.com and let me know where they're listening to the audio cassettes. So if you've got a real strange place that you're listening to the audio cassettes, let me know, because I would like to send you a real nice QSL card. So if you're listening to them at a unique location, maybe even get a picture, and I'll send you a confirmation QSL card that, yep, that's pretty strange, listening to the audio cassettes wherever you're listening to them. You'll get a nice QSL. So let's have fun with this. All right, time to take a break, and then we're going to jump back and do a little bit of multiplication. So keep the kids' calculator handy, take a break, and I'll meet you back at question E5G11. Take a break. Hi there, welcome back. I said take a break, not a vacation. Holy mackerel, you've been gone a long time. This is Gordo, WB6NOA, and welcome back to Extra Class Test Preparation. And you know, we're more than halfway there. In fact, now it's pretty easy because we've already got that tough stuff already down on our audio cassette number 3 if you're listening to us on tape cassette. And now it's pretty easy. So let's take a look at a simple formula, and that is true power is equal to volts times amps times power factor. That's not very hard, right? True power, E times I times PF, power factor. Let's just say that for question E5G11, they give us a power factor of 0.2. No problem, write that down. Voltage is 100 volts at 4 amps. Hey, this is easy. Clear the calculator. 100 x 4 equals x 0.2 equals, and you should have 80 watts, right? Hey, not bad. Boy, give me more of these easy ones on the exam. Sorry, that's all you get on that one. Finally, why would the power used in a circuit be less than the product of the magnitudes of the AC voltage and current? Well, that's because there's a phase angle greater than 0 between current and voltage. So the power used in the circuit will actually be less than the product of the magnitudes of the AC voltage and the current.
I'm headed back to the shop right now.
Well, we've tuned into a repeater, and the repeater is doing just a great job of coming through because we recently replaced the antenna system. And they have several questions about the effective radiated power of a repeater as it relates to losses and gains. And let's take a look at these questions now so that when you go up to the repeater, you'll be all set to determine how well that system is working on both transmit and receive. Question E5H01. What is the effective radiated power of a repeater station with 50 watts transmitter power? Need to write that down, 50 watts. 4 dB line loss, 2 dB duplexer loss, 1 dB circulator loss with a 6 dB gain antenna. Well, first let's add up all of the losses. Okay, 4 dB and a 2 dB in the duplexer. Now we're 6 dB loss. And another dB loss in the circulator. Now we're 7 dB, offset with a 6 dB gain antenna. Well, that means we have a 1 dB net loss that's affecting our 50 watts of transmitter power. Now, on page 138 of my book, and you only need to know just a couple of the dBs, and some are easy, the 1 dB loss is like a 1 1/4 change, and the decimal value of 1 dB lost is 0.794. So multiply 50 watts by a slight 1 1/4 loss, 0.794, and that works out to 39.7 watts effective radiated power. In other words, after suffering a dB loss, that 50 watts now sounds like it's 39.7 watts. All right, let's try another one. Let's start with a 50 watt repeater transmitter, 5 dB line loss added to 3 dB duplexer loss, that's 8 dB, and another dB in the circulator, that's 9 dB loss with a 7 dB gain antenna. Well, in this particular repeater installation, we have more loss than gain. In fact, if you add up the losses, we have 2 dB more losses than gain. Now, on page 138 of my book, 2 dB loss is a 1.5 times change, and the decimal value for 2 dB loss is 0.633. So multiply 0.633, which is a 2 dB loss, times the 50 watts, and you end up with an effective radiated power of 31.5 watts. All right, now let's try a 75 watt transmitter, 4 dB line loss, and a 10 dB gain antenna. Whoa, boy. 4 dB line loss, 10 dB gain antenna. This gives us a 6 dB gain. Now, we know that when it's 3 or 6 or 9 or 10 dB gain, we can do this in our head. 3 dB is a 2 times power change. 6 dB gain is a 4 times power change. 9 dB is an 8 times power change, and 10 dB is 10 times. So this one is 6 dB, which is 4 times, so multiply 4 times 75, And your correct answer is 300 watts. Well, that was pretty easy. Let's try another one. 75 watt transmitter, 5 dB line loss, 3 dB duplexer loss, 1 dB circulator loss. All right, that's 5, 6, 7, 8, 9 total loss, 6 gain, which is a 3 dB loss. Now, 3 dB loss is a 2 times power change. So if we started with 75 watts, half of 75 is 37.5 watts, or 37.6 is the correct answer. All right, you're doing great. How about a 100-watt transmitter? 1 dB feed line loss. Now we've got a nice setup here, and a 6 dB gain antenna. Well, the 6 dB gain antenna will give that 100 watts the effective radiated power of 400 watts. But we've got 1 dB a line loss, so we multiply 400 watts times 0.794. That's at 1 dB loss, and that comes out 316 watts. Just be sure and remember 0.794 is minus 1 dB, or 1 dB loss. All right, let's go for the effective radiated power. Peter, 100 watts. 5 dB line loss. Ooh, that's pretty high. 3 dB duplexer loss. Wow, that's pretty high. That's 8 dB. 1 dB circulator loss. Now we're down to 9 dB. And a 10 dB gain antenna. Oh, that's a gain. Well, we know we're a little higher than 100 watts with 1 dB gain, and you have only one answer, 126 watts. That is the correct one. But if you'd like to actually do the calculations, you'll find in my book I give you the dB calculations. But 1 dB gain is multiplying 1.259. But you don't even need to do that, because looking at the answers, you'll see that there is only one that is slightly over 100 watts of ERP. So that one you can do in your head. Let's try another one. 120 watt transmitter, 5 dB line loss, 3 dB duplexer loss. Now we're up to minus 8 dB. 1 dB circulator loss. Now we're down to 9 dB with a 6 dB gain antenna. That is a net loss of 3 dB, so it cuts our power in, that's right, in half. So the answer is 60 watts. All right, let's try 150 watt transmitter, 2 dB feed line loss. Oh, this is a good one. 2.2 dB duplexer loss and a 7 dB gain antenna. Total loss 4.2 dB. Total gain 7 dB. This is an approximate 3 dB increase, 3 dB overall gain, and it almost doubles your 150 watts. So it's not quite 300 watts. The closest answer, slightly less than 300 watts, is 286 watts. Again, you can do this one in your head. How about a 200 watt transmitter, 4 dB line loss, 3.2 dB duplexer loss, 0.8 dB circulator loss with a 10 dB gain antenna. All right, first add up the losses. Comes out to a total loss of 8 dB, total gain of 10 dB. So we have a net gain of 2 dB. Now, 2 dB gain is multiplying the 200 watts by 1.585 found in my book. And that comes out with, we start with 200 watts, the answer is 317 watts. Well, let's say you completely space out and you forget what to do. Well, we know we have 2 dB gain. 3 dB gain is 2 times, so it's going to be less than 400 watts. And we started off with 200 watts, so what do you have between 200 and 400 watts? Well, they changed it. Looking at this from the old extra test, now they've got one answer at 300 watts and one at 317. Woo-hoo-hoo. So no calculating in your head this one. It's 200 times 1.585. Now, in my book, I give you the actual dB calculations if you want to work it that way, or if you want to simply go by the page in my book that shows 1 dB gain at 1.259, 2 dB gain is multiplying by 1.585, 1 dB loss is multiplied by 0.794. 2 dB loss multiplied by 0.633. And remember, 3 dB is 2 times, 6 dB is 4 times, 9 dB is 9 times, and 10 dB is a 10 times power change. All right, check these over. You'll probably have maybe one on your upcoming test. Let's try one more just to see how you do. Effective radiated power of repeater station with 200-watt transmitter, 2 dB feed line loss, boy, that's acceptable, 2.8 dB duplexer loss, 1.2 dB circulator loss, made up with a 7 dB antenna gain. All right, let's see. Our losses add up to 6 dB loss, and our gain is 7 for an actual gain of 1 dB. All right, this would be a slight increase to our 200 watts output in effective radiated power. So ERP is, if you work that out, there it is, 252 watts. This one you can do in your head because 200 watts with 1 dB gain, they have no other answer slightly above 200 watts. They got 600 and then a couple below it, but only one answer, 252 watts. What does the term describe station output? Now that's transmitter, antenna, and everything in between. When considering transmitter power and system gain and losses, that is called effective radiated power. And in my book, I point out good coax cables to use up at the repeater site. And take a look, if you use inexpensive coax cable, you're going to suffer a lot of losses. You don't want losses. E5H12, back to reactive power. They just wanted to throw that one in again. Remember, that is wattless, non-productive power. Now, we talked about the power factor, and we talked about the phase angle. You need to know a couple of them for the last couple of problems before we take a change over to E5I, photoconductivity. E5H13 says, what's the power factor of an RL circuit having 45-degree phase angle between the voltage and current? Now, you remember that earlier problem where we had 60 degrees? 60 was, that's right, 0.5. 45 degrees is going to be 0.707 if you don't have a calculator. 60 degrees is 0.5. What do you think 30 degrees would be? 30 degrees would be 0.8. So 60 degrees is 0.5. 45 degrees is 0.707. And 30 degrees is 0.866. So the less the angle, the numbers are going up. 60 degrees, 0.5. Remember 60, driving 65 miles an hour. 60 is 0.5. 45 degrees is 0.707. And 30 degrees is 0.866. Now, how many watts are consumed in a circuit having a power factor of 0.6 if the input is 200 volts at 5 amps? E times I times power factor. 200 times 5 times 0.6 comes out 600 watts. Let's do one more. How many watts are consumed in a circuit having a power factor of 0.71 and the apparent power is 500 watts? Well, 500 watts, multiply that by 0.71 and you end up with 355 watts consumed in the circuit. Okay, put that calculator away. You won't need it for the next few questions. And you know, on your upcoming extra class test, as we're going to describe in the last portion of our audio course, we're going to tell you how to sort of brain thump the correct answer, even though you completely forgot what the specific formula might be. We'll show you how to try some different things to see if the right answer pops out. So don't be overly concerned if you're not able to memorize all of the formulas. You're going to do okay. And remember, you only have one question out of each one of the groups. And this group that we just covered had 16 total questions in the pool. Only one will be on the test. And now let's take a look at the group photoconductive principles, E5I. Chances are you already know about photoconductivity, remembering that a photocell has high resistance when no light shines on it, and a varying decrease in resistance when light does shine on it. And it can be in an on or off state as a simple beam alarm across a doorway, and the photocell is many times found in the modern digital cameras as a sensitive light meter to judge the amount of light present. What is photoconductivity? That is the increased conductivity of an illuminated semiconductor junction. Increase of conductivity. What happens to conductivity of a photoconductive material? When light shines on it, it becomes more conductive, or it increases. What happens to the resistance of a photoconductive material when light shines on it? Well, just the opposite, it decreases. What happens to the conductivity of a semiconductor junction when light shines on it? Same thing, it increases. And in your modern worldwide radio, and we'll go ahead and we'll turn on the modern worldwide radio, and we'll turn up the volume here and get a little radio reception. There we go. In this modern radio, as I turn the tuning dial, it's not actually tuning a big capacitor like we used to do in the old days. It's actually tuning a circuit that interrupts light, and that circuit is called an optocoupler. And they ask the question, what is an optocoupler? That's a light-emitting diode and a phototransistor. And the optoisolator is a light-emitting diode and a phototransistor. So optoisolator, optocoupler, same answer. What is an optical shaft encoder? Well, that's an array of optocouplers whose light transmission path is controlled by a rotating wheel, and that wheel has dark spots and light spots for light either to be blocked or to shine through. What characteristic of a crystalline solid will photoconductivity change? It changes the resistance. And what material will exhibit the greatest photoconductive effect when visible light shines on it? The very best is cadmium sulfide. Cadmium sulfide. Think of your new handheld radio with a NiCad battery. Cadmium sulfide. What material will exhibit the greatest photoconductivity effect when infrared light shines on it? Well, not cadmium for infrared. For infrared, it is lead sulfide. Lead sulfide for infrared. All right, now say these out loud, and if you're on headphones, people around you will think you're very strange. Say cadmium for visible. That's right, cadmium visible. Come on, say it. Cadmium visible, lead infrared. Lead infrared, cadmium visible. Cadmium visible, lead for infrared. Got it? Which material is affected the most by photoconductivity? That is a crystalline semiconductor. Remember, up in the space station and the space shuttle, they're trying to grow crystals because they're used so much in radio circuits as semiconductors. What characteristic of optoisolator is often used in power supplies? Well, they have a very high impedance between the light source and the phototransistor, so they won't load down any of that circuit. And what characteristic of optoisolators make them suitable for use with a triac to form a solid-state equivalent of a mechanical relay for 120 volts AC household current? Well, optoisolators provide a very high degree of electrical isolation, keyword isolation, between a control circuit and a power circuit. All right, it's time to take a well-deserved break, and then we got just a few more minutes, and then we'll take another break, and then we're going to look at all of these little pieces of circuitry that I have right here in this box. So take a break, and I'll meet you back here in just a few minutes when I get my box of goodies ready. Hi there, back again with my box of goodies here. That looks like a whole box of little ants. Well, let's take a look and see what's inside this little box. All right, in what application is gallium arsenide used as a semiconductor material in preference to germanium or silicon? And yeah, that was hard to say. Well, we use them at microwave frequencies. Microwave frequencies is the correct answer. And what type of semiconductor material contains more free electrons than pure germanium or silicon crystals? That is N-type. There are more free electrons orbiting the nucleus. It is an N-type material. Now, do you know the majority charge carriers in P-type semiconductor materials? The majority charge carriers are holes. The charge carriers are in abundance in P semiconductor materials. They are holes. Now, do you know the name given to an impurity atom that adds holes to a semiconductor crystal structure? Well, that is called acceptor impurity. That's the impurity atom that adds holes to a semiconductor crystal structure. Now, there's a good chance that you'll have one question from a group of questions about semiconductor materials. Now, before we take a break, I want you to remember the phrase "and free" for an N-type material where antimony atoms or arsenic atoms have been added. And free. And there'll be more free electrons, that's the free, in an N-type conductor. And free. Antimony atoms or arsenic atoms, more free electrons, N-type semiconductor. And free. Now, Plumph, much like sneezing, is a P-type material produced by adding either gallium or indium, producing more potholes than free electrons. Think of P-I-U-M-H, Plumph. Also, anything that provides as a P in it as a donor, and an acceptor impurity will add holes. Got it? Good reading about semiconductors can be found in a lot of the technical books on semiconductors, but remember the name given to an impurity atom that adds holes is called an acceptor impurity. The only answer, add holes with A in it. P-type semiconductor, the majority charge carries in it holes and more free electrons than pure germanium or silicon crystals. That semiconductor material is free, and free is N-type. All right, now let's take a look at the alpha of a bipolar transistor. Now, in bipolar transistors, the term alpha is a variation of collector current with respect to emitter current. Key phrase CCEC, collector current with respect to emitter current, CCEC. Answer C, the change of collector current with respect to emitter current. That is the alpha of a bipolar transistor. Now, we want you to take out figure E6-1. Visually impaired, you don't need to worry about this one, but take a look for the rest of us at E6-1 and look at those little transistors, because we're going to be coming back in just a moment and asking you which one is NPN and which one's PNP and all that kind of stuff. So I'm going to go ahead and work a little DX. Now it's time to take a break. Now don't take a vacation, just take a little break. For those of you on audio cassette, I will meet you back here in just a few hours. So everybody take a break and take a look at figure E6-1 in the meantime. And I'm going to go out there and work maybe a little bit of DX. Take a break.